Hello everybody, welcome to the AES lecture. Before I start, could you just make sure you've got your phones turned off, please? You probably have, you all know what you're doing. If you're here as an SAE student and you know us through the student event that we did last Saturday here, we actually do this every month on the second Tuesday of each month. So next month we're moving to a different location and I'll do the parish notices at the end and talk about when that's going to be. For the time being, to warm us up on this wintry evening, we have a talk about thermionic valves from Rob Toulson on your right, my right, your left, and Charlie Slee on your left, my right, the other way round. So I'm not going to shorten your time anymore by talking, and I'll leave you to it. Thank you.
Thanks. Yeah, I was going to open up actually. So I'm Rob Toulson. I actually run and lead the Cambridge Audio Engineering Society section, and I've known Charlie for a good few years actually, and he did this talk for us up in Cambridge last year, and it went down a storm. So Bill actually invited us to come and do a similar talk here in London, and actually since then things have moved on a bit. We've been collaborating on a few things for quite a while, and so we're gonna just talk about not only what Charlie's been doing and what he presented last time, but also some of the research that we're doing and looking forwards into hybrid analog systems, analog digital systems. So, I mean, he's gone on to the summary. But basically, yeah, I'm predominantly a digital engineer. My research is in signal processing and digital audio systems. And Charlie's clearly an analog engineer. And actually, I've known Charlie since he was studying. And it's incredibly difficult these days to teach electronics based on thermionic valves because we just don't have the facilities, we don't have the health and safety allowances and so on. So actually it's becoming, in terms of education, a bit of a dying art. And I know Charlie basically took it on as a labour of love that he wanted to get into thermionic valves and effectively had to teach himself because there wasn't anybody in academia who was actually in a position to teach him a lot of this stuff. So I know he went off and did a few apprenticeships and has ended up working for a few years for Thermionic Culture and making some of the best regarded valve gear in the world. And so I think that's brilliant to have him sort of telling us a bit about his journey and what he's working on. So just a little summary of what we're going to cover. Basically, Charlie will talk about distortion, a few of the thermionic bits of kit, why we still use valves, and then at the end I'll talk a little bit about some of the research we're doing in looking at hybrid analog digital systems and how these kind of bits of equipment can still be sort of viable in the modern sort of approach to music production and recording studios, because clearly there's a challenge there in making sure that these things still integrate in the tools we use. So I'll pass you straight on to Charlie, who will talk you through everything thermionic.
Thank you. Well, the idea for this lecture was to give a better insight into valve technology for a number of reasons, really. I think it's really important to have a good understanding of the electronic circuits you use when you're recording and mixing, and having a better understanding of how the valves work and how they distort will benefit you during your session. For me, it's also important to fly the valve flag. I still believe they're the best device for amplifying music, and I think it's really important to keep that technology alive. So I don't really want to go into the physics of the valves, how they work themselves, but I think it is important to understand their characteristics and how we can manipulate those characteristics for use in the studio. So if we look at these two very similar circuits, this is the basic building block for your electronic valve circuit. We apply a HT high voltage to the anode via a resistor, and we need a negative voltage on the grid with respect to the cathode, which is at the bottom. And this is done in two ways here. On the right, we've applied a negative bias to the grid, and on the left, we have actually just biased the cathode higher than the grid. This is the basic building block for any circuit, and obviously there are much more complex elaborations on this, but we can use this to show how a valve amplifies. So, looking at a basic data sheet, this is the ECC83, probably one of the most common small signal triodes, double triodes. And this data sheet tells us all sorts of useful information, typical characteristics and heater current requirements. It also shows us some very useful curves. So these are the anode characteristics graph of the ECC83. And here we can see current through the anode by anode voltage at different negative grid voltages. So, moving on before I bore you completely. We can pick our load line here, and this is actually a really useful diagram from the Valve Wizard, which is a brilliant site if anyone is interested in this kind of thing. We can see our negative grid lines and our input signal or our audio, our music. We can see the full cycle of that on the -1 volt line. And we can also see how this corresponds on the valve's anode. And this is really one of the beautiful things about valves, is that we have a very small current change producing a very large voltage swing on the anode, so we have lots of gain very cheaply. But we also have it very cleanly. So let's not get too caught up in this, but it is important to show how this affects the distortion in your recording stage. So we can see that if we're still taking this input signal we have on our grid, we can see that it's happily swinging through positive and negative cycle up to point D and then down to point B. But if we were to have a bigger input signal, we would need to go up to point E, for example, and down to point A, and you can see that the lines don't exactly start matching up as well. They're not as linear, they're not as equal. And things like this will cause unlinear distortions. Other ways of distorting your signal would be to reduce the anode voltage to anode cutoff, or maybe you can appreciate that if the signal was so big that it went above E, above your 0 volt line, that the valve will actually will be forced to draw grid current. And I don't have a picture of it now, but you can imagine that this is how your signal starts getting cut off. These are both effective ways of producing distortion, though. I mean, all classic guitar amplifiers will use either grid current limiting or anode cutoff to distort the sound, and that's where the valves really shine in distortion. But of course, if you're building a microphone amplifier, a power amplifier, or a line amp, or a mixing desk, you will want compressors and summing mixers, you will want the most linear amplification. So you want to find regions where your signal will be amplified equally throughout its full 360-degree cycle. You can actually see a quick bit of maths for you. Here is a 1 volt sine wave on the similar graph. We can see that the anodes are swung from 195 volts to 130 volts with a gain of 65. That's shown in decibels as 36.3 dB. If we added if we had a 2 volt peak to peak sine wave, so going from point C all the way to point E and back down to point A, when the grid swings from -1 volts to 0 volts, the anode swings with a gain of 71. But when the grid swings in the other half, there's only a gain of 59. So this is creating distortion. You can see that as 4.6 second harmonic, which is huge. So that hopefully shows the importance of selecting, when we're designing the circuits, the right load line and making sure that we have the cleanest amplification. Of course, we maximise things like this in the Culture Vulture, which now really is an industry standard distortion unit. And when I first started at Thermionic Culture, it seemed completely mad that you would have a unit that added distortion to your tracks. I just couldn't figure out, coming from a school of the hi-fi area where I wanted it to be as clean as possible, this just seemed bonkers. And especially when people are using it across their mix buses, and I know that is it Ken Thomas, the producer that did Sigur Rós? Is that his name? Ken Thomas? He uses this on almost everything, and you can listen, when you listen to TAC by Sigur Rós, you can almost hear that. It's very subtle, but yeah, so it just didn't make sense to me at the time. But we have a very similar setup to creating distortion as that graph before. So there's a bias control, and that is a resistor, a variable resistor in the cathode of the distortion valve, and the meter is showing current through that valve, and you can be very creative with it. We also have some filters around the pentode, so there's different pentode settings for all these ludicrous waveforms that you can get out of it. But you know, it's worth considering. This distortion, I think, is very important. It's worth considering when you're in the recording process or mixing process, because you need to consider you should really consider your input signal and the input and output attenuation, and for what colours you want to create. So why do we still use valve circuits? Well, I think that the solid-state designers have been trying to catch us up for the last 40 years, and now they finally have. The quality of valve amplification and the colours you get from driving the valves into distortion is still very important in the recording and mixing process. We wouldn't build an all-valve mixing desk now. There are some out there, but there really is no need. At Music Messa last year, I saw one channel of a SSL style desk that was all valve, and it had 24 valves in this one channel. The full-size 64 channel desk had over 1,000 valves, which makes heater current at about 300 amps. It was an engineering triumph. It was beautiful, but it was just completely crazy. There was no need for it. And I think as manufacturers we need to consider the efficiency in the environment and also the affordability of running the products we make. So even if this desk did sound fantastic, and you'd hope it would, I think it cost about €1 million to make. It's still insane. So let's use valves where we need to and use solid state for the rest. One of the most obvious and unique ways we can use valves' natural characteristic in the studio is the vari-mu compressor. So if we take a classic vari-mu design, which is the Altech 436C, it's the obvious example and is actually the starting point to our Phoenix. A vari-mu compressor works by a valve's natural characteristics, using the valve's natural characteristics to compress the signal. So all valves will reduce gain with reduced bias current, and normal valves like the ECC83, when you reduce the bias current, there won't be a significant effect. But if we use valves like the PCC85 that we use in the Phoenix, we only have to reduce the bias current a little to have a significant effect in gain reduction. And a vari-mu valve, so a vari-mu means variable mu or variable amplification factor. So a variable amplification factor under different conditions. So if we can just have a look at the, I'm not sure how much you can see from here, but this is the anode current characteristics of the ECC83, and this is the PCC85. Hopefully you can appreciate that at different grid voltages there is a more pronounced swing, and it's quite unfair because there is the X and Y axis isn't quite the same, but hopefully you can appreciate that. So essentially by changing the voltage at the grid we can vary the amplification of the first stage, or we can vary the compression. So how does the Altech do this? This is a very old circuit. I think this is mid-50s, maybe later, I'm not too sure. So without going into too much detail, we can see that there is an input transformer at the top, followed by two valve stages in push-pull, and then an output transformer. And we can see that we have tapped the primary of the output transformer, and this is being rectified. So what we're doing is we are taking your AC signal or your music and rectifying it to a DC voltage, and then that is fed all the way back to the grids of the input valve. So depending on the threshold, depending on the size of your signal, it will in turn create a larger or a smaller voltage at the grid of your input valve, and therefore compress your signal. So we have a, there's no sort of clever circuitry here really, other than just this one aspect of this feedback sidechain, which is it just seems very natural and very simple. Obviously more modern designs will have threshold and attack and release. You can actually see the release, it does have a release dial here. The way you see the compression is a reading of the current through this valve. So we set up our Phoenix to run a certain current through the compression valve, and that sets to 0 dB gain reduction. And when that valve starts drawing less current, we can match it to a decibel scale. So really we've just used a handful of parts to create one of the world's best and renowned Sofny compressors. And this is one of the most beautiful aspects of the valve circuit design. You look at a design like this and you might think, well, if I was handy with a soldering iron and knew basic electronics, I might attempt to put one of these together. And sort of, I still want to sell you these, obviously, but it's a very interesting journey, and there's lots of companies out there still that make very high quality components like Salter transformers, which is just in Ipswich. And there's a huge resource online for DIY projects. Of course, you've got to be careful with the high voltages. They can be dangerous. You've got to be more careful than I am, anyway. So let's move on to the busted. So actually, similarly to this, I think one of the reasons that valve circuits sound as good as they do is because of their simplicity. So there are very few components in the signal path, and due to the valve's natural linearity, we need very little to no negative feedback. The electronics geeks will appreciate the use of negative feedback to increase performance in audio circuits. We would expect much lower distortion and higher bandwidth at the cost of reduced gain. So we've actually taken that concept into our fat busted mixer. We have an attitude switch, the big red dial, that goes from 1 to 6, and that effectively is reducing the negative feedback applied to the circuit. So it's a very simple concept, but it produces very nice results. So as we go from 1 to 6, we're reducing feedback, which in turn increases gain and increases the distortion of the valve, the natural distortion of the valve, which is predominantly second order. This would, of course, be possible with transistors, but it wouldn't sound as good, putting it nicely. Many valve mic amp designs use similar circuits, actually, so where the input gain control will control the feedback to the circuit. So on low gain settings, the amplification will be the cleanest with maximum feedback. And at the highest gain settings, there will be little or no feedback, and therefore higher gain and higher distortion. So it's certainly worth thinking about that if you're recording using valve mic pre's, what sort of tones and colours you want from your recording. I can do a quick demo with the Busted. I've got a recording that Rob did for the Medieval Babes. I'm just going to quickly play something and go up the attitudes. I'll try and back off the output level because obviously the level's going to go up, and that might make you think that it sounds better by just it going up, which sometimes happens, but hopefully you can hear the distortion from the natural distortion from the valve, and actually it's not too much. I mean, it does say max, and it's got a big attitude and a red knob, but you know, hopefully it doesn't sound too full on. So hopefully you can hear that wasn't actually too much, you know, it wasn't too full on. And the interest, we do have, it's not as simple as that, where there is other circuitry around it to manipulate the frequency response, but we are essentially just using the valve's natural distortion to create that tone. Yeah, by all means you can come and play on these later if you wish. Okay, so looking forward, one thing I'm passionate about is securing the future of valve technology for the next 10, 20, 50 years in pro audio. And now that the solid state guys have finally caught up, I think it's important that we develop new ideas. And most importantly to me, begin to integrate valve circuitry with the digital domain and with digital automation to bring it fully into the recording studio of the future. So digitally controlled analog is nothing new. Many companies have done it, some still do, but none are actually doing it with valves in pro audio. One approach that we are looking into would be to use some relay attenuators instead of your variable resistors. Now these can be controlled by a potentiometer, an encoder, a digital source or an infrared signal. Now if we keep the device, if we can control this device from a distance, then we can keep signal wire lengths down, and we can even keep sensitive signal circuitry away from noisy power supplies and other interferences. And if we can control this device digitally, if we control this by a digital source, we can have full control and recallability. So not only do we have a device that brings our 100-year-old circuit into the future, but we have improved its performance as well. We'll just quickly swap this over. This is the Dscope that we use for a lot of testing. Oh, it's not yet. Do I need to do anything to that?
Only take one.
I'll just carry on anyway, shall we? We use the Dscope for all our test purposes at TC. There we go. So this is the Phoenix, one channel of the Phoenix. You can see the gain is, so the level is at 4 dB. And this is our distortion, 0.04, which is pretty good for a valve circuit. During the test procedure, we have a potentiometer in the cathodes of the output stage of the Phoenix. And this is a really useful and accurate way for us to set up the unit for the lowest distortion. So I'll just quickly change it. So you can see here that all the way around we're not amplifying very well at all here, 0.7, 1%. So what we're doing here is, in our test procedure, we will find the lowest distortion point, which is usually about 0.02. It's actually usually a lot lower than that, but this is a bit old. So we'll do this, and we'll come back to it in 6 hours' time and 6 days' time, and make sure that it's still there, because valves have a tendency to drift, and we need to know that every unit that goes out is going to be perfect for the end user. The trouble is that in a year's time, this may not be as accurate as when it left the workshop. We've had Phoenixes that have come back that have been 3 or 4 years old that have still been very good, and we've had Phoenixes that have come back that have only been 6 months old and they've been very poor. So it's important for us to make sure we get this right. I mean, we pick the valves very precisely to make sure that this doesn't happen. But one option would be to use the relay boards that I just mentioned, and we could have an onboard testing procedure. We could use DSP to create a self-automated test procedure. We could have a program designed very much like our physical program to find this lowest distortion point. It could send a test tone through the circuit, analyze it using FFT, and realign this potentiometer to the lowest distortion point, effectively setting up your Phoenix or your compressor to be perfect for every use. And this could happen at the click of a button, essentially. I mean, the advantages are quite varied as well. We've also extended the valve life as well, because we might say that if it starts drifting too much, the valves are no good. But if we have this procedure that automatically configures it every time you use it, then we could extend it for another couple of years. And of course, like I said, you'll have a perfectly balanced unit every time you use it. There are certainly a lot more benefits to this. This is really only just touching on it. And of course, we don't have to restrict ourselves to valves. We could use it with any circuit. And it will really just be up to the next generation of engineers to take this and run with it. But I'll now pass you back over to Rob, who's going to take this a bit further. I'll just plug you back in, shall I?
Yeah, actually, I was just going to, yeah, if you just really pick up where Charlie's left off with talking about these advantages that we potentially foresee if we can integrate some of these types of bits of gear with some of the benefits that we can get from digital systems. I mean, there's a list there. I mean, some of these are not always valve versus transistor questions. They're often software versus hardware questions, people mixing in the box versus people mixing with hardware, and actually more often than not people who want to do both at the same time. I think the point Charlie's made about having some kind of automatic calibration within a system that by definition deteriorates or changes its characteristics over time is potentially a really fantastic kind of idea. What else have we got there? Actually, I mean, and again, Charlie's touched on this, that actually these things need to integrate with digital systems, because the modern recording way is digital predominantly, certainly in education, in terms of how we teach people. Everything's using DAWs. We're often using digital plugins. Very much there's a generation of music producers and sound engineers who are coming away without the skills to know how to use these things, and often the best way to know how to use these things is to understand how they work. So actually that kind of skill's kind of getting lost. And so I mean, when I was at the AES convention in San Francisco, I saw a slight divergence in the technologies. It felt like the analog guys had tried to engage in digital, and the digital guys had tried to engage in analog, but actually more recently they've kind of gone the other way. And there was some phenomenal pure analog mixing desks at AES San Francisco, and as if they'd said, look, this is what we do, we don't understand what you guys do, so we're just going to do what we do and keep doing it. And I don't know, I obviously prefer, from my own personal perspective, a kind of a more mixed approach. What else have I got? Total recall of settings. I mean, as a mix engineer myself, gone are the days of booking a control room, sitting in there with the artist, mixing, bouncing it down, and then that's it. That's the version that gets cut to the CD. That doesn't happen. Nowadays we work remotely, we work in less expensive locations. I tend to be mixing, send some files out to the artist, they'll then come back to me with comments and they'll say, yeah, brilliant, nearly there, can you change this? And so on. So the next day I then have to pull the session back up, change something. The more we use this, the more difficult that gets. So actually, I was just thinking on the way over this, I mean, these aren't cheap bits of kit, they're very expensive, but actually the problem isn't what they cost, it's what they cost to use. That is the problem. They take longer to use, they take a more sort of a more manual approach, which I think is great, but clearly the music industry isn't sort of supporting that amount of revenue. What else have we got? Syndication of design. I mean, Charlie mentioned there is a hell of a lot of audio signal that goes to the front panel, through a potentiometer, and then back to the circuit board. So there's a lot of wiring in there, which if we could make this front panel digital and keep all the analog wiring shorter lengths, hand wired, less complex, there's actually benefits to that. As well as a number of other things. Sharing of data, metering, signal analysis between devices. Potentially, if I could communicate with these devices through a digital system, I could then send all the metering data back to a host, and I could actually look at all my gain control on all the devices in a digital context, because the metering's just data. In fact, in Charlie's designs, the meters actually sit in the signal path in some instances, because they actually become a key component on, and they can actually be a key component on the sound of the audio. Whereas actually with signaling, we sort of just want to look at it without changing the source. So we anticipate a number of benefits of trying to move to this, and obviously a number of companies have looked into this already, and obviously we now have SSL do this very well, and they clearly are trying to support this approach. The pure analog mixers, which have full digital control, are sort of well regarded in the industry, but they're also doing quite a lot with digital patch bays, so patch bays that have digital control. And actually, I think there's some new interfaces from SSL out recently, which are really focused on supporting the analog summation kind of approach, the kind of things you'd use this for. Yamaha and actually in live sound, I think it's not uncommon now for iPad controlled devices. So we're looking all the more at remote devices and being able to change the settings from somewhere else. In fact, in a studio like this, that's often quite a challenge, because there might be a rack over there with all my expensive analog outboard gear, and I'm sitting here at the mixer performing a mix, and I think, oh, I need some compression on the vocal, so I run all the way over here, change the compression on the vocal, and then come back here and have a listen, and it needs a bit more, so I go all the way over there and come back, and actually just that can be enough to disrupt a mix session. It can be quite a challenge. Which is clearly what there's the source of my image. This Bettermaker device is fascinating and was on show at the AES convention in San Francisco. And this is very similar to what we're talking about here. This is an analog EQ that is fully controlled by a digital front panel, and it's got a USB control with an interface, so you can actually plug that in as a plug-in. In fact, there's even a version without a front panel on it, so it's completely analog circuitry, entirely within your mixing session, but with literally digital controlled and software controlled knobs and buttons. So what supports this? Myself and Charlie have been working with this with Lucas at Elmer, who makes some of the components that are in those hybrid analog digital systems, and we've got some of these here. I mean, these are these relay attenuators that Charlie's mentioned, and effectively what we've got is on the top half we've got a whole ladder of relay controlled resistor network, so we can attenuate with that. Basically they're just volume controls, and at the bottom here we've got a little bit of microprocessor control that we can actually set those. So effectively all this is a digital volume control, but it can have a lot of it can bring a lot of enhancement to something like this. So for instance, we've got our drive and our trim controls on the Phoenix. Potentially they could be, these potentiometers which have signal going in, signal coming out, could just be controllers for something like this, which is actually doing the attenuation. It keeps the audio well away. We can move the audio well away from the transformers and things like that. I don't know, we're still experimenting. I was just going to I've got some examples that were this video is not that exciting, but I might as well show you it. So this potentiometer is connected to a microprocessor, sending a serial communication to the relays, which are really then just implementing a ladder network. This little display just shows where it's at, and we're now at the stage where we can start plugging audio into it and making sure it works properly. That's that. We've got some of these you can have a little look at afterwards. So, that's that again. So where are we at? This is pretty much where we're at. Oh, you can't read that. It says potentiometer. So this microprocessor, actually it's not the one that's on the demo, but I use the Mbed microprocessor. It's a bit like the Arduino boards, if anyone's used Arduinos. Slightly higher capability than the Arduinos, built by ARM, got one of the ARM M3 chips on it. So that can read a potentiometer input, and then it can send some serial data to a device like this and tell it what settings to go to. Which isn't that exciting. It's not very advanced. My next slide is going to be not very good. Okay. So, but what we can do is add lots more capability to that. What I've got in the top left corner is a Bluetooth module. Basically, I can connect a Bluetooth module to this Mbed, and now it can be controlled by an iPad or anything which has got Bluetooth interface. This is motorized potentiometers, which can actually give readings, but also if we change it by the iPad, they can always be in the right place and always showing the correct setting. What's this? Switches, as well as controlling the attenuation of the signal flow. We can also control LEDs, brightness of LEDs with light-dependent resistors, and actually take out some of that signal flow from in the variable resistors in the valve circuitry. So we do quite a lot with that, and actually that's where we could potentially change the biasing. So we could have the microprocessor actually in some way reading the audio, looking at its distortion characteristics, and then outputting to an LED LDR system and changing the biasing on the fly. So you could either do that automatically, or you could do it as a sort of a calibration that's set up. What's the top one? Front panel meters. Yeah, once we start doing this, these meters no longer have to be analog. I mean, we like them analog, they're good, we like wobbly needles, and we like the sort of the realism of it. But potentially it could be a digital meter, because now it doesn't have to actually evaluate the signal in an analog context. So that's what we're doing, and that's where we're going in terms of this kind of collaborative research project, and I suppose we've already alluded to the fact that really we got this philosophy that we'd like to try and build a digitally controlled or a remote control Phoenix, and you know, we sort of have different motivations for that. Like I say, Charlie's actually very keen to make sure that these types of devices don't get lost in the future of the music production industry. They are very expensive, they are very bespoke, and they are difficult to. They do bring an overhead of time and functionality in terms of your mixing process, you know, so we're going to do it anyway. But we don't really stop to think whether we should, you know, or whether it's actually what people want. But anyway, we're engineers, so we just build things because we like putting technology together and seeing what happens. We'll see how it goes. Maybe we'll update you in a year, 2 years. I think that's about it for now. We just sort of wanted to open that up to questions at that point, because, you know, hopefully we've kind of touched on some things. Raw analog, please ask Charlie questions about raw analog and the design of these things, and if you want to ask about our project and what we're working on and what we're thinking, and tell us that we're crazy or whatever, then please do. So thank you. That's it. Our talk. I've got a load of little. My demos don't look as cool alongside Charlie's, I'm afraid. They're not quite so exciting, but they're here if anyone's interested in this side of things. Normally we don't talk to each other, but you know, we're sort of like, how did you describe it?
Forced marriage.
A forced arranged marriage of some description, but we'll see what happens. So thank you very much. So, any questions for Charlie, I'm sure. Hi.
Charlie, I've got a question. You said on a couple of occasions that the solid state boys had finally caught up. What's given you that impression over the last?
I think, the first time I did this lecture, I slated the solid state circuits quite a lot, and realised that actually they are very good, you know, and there are a lot of very good circuits and designs out there, but I think that there's been very, very poor ones, and they have finally got to a point now where they can compete with us on sonic terms. I think that, you know, I don't want to get too involved with distortion. That, you know, when people look at valves and they talk about valves, they'll say, oh, that's really warm and coloured, but actually if you want it to be very clean and amplify well, it will, and it will do it as good as any solid state circuit. Did that answer your question? Or?
What angle probably go a bit further, just to say, I mean, do you mean that the solid state boys can replicate everything you do with valves, or that they do certain things that you can do with valves?
Well, they can obviously do a lot more than we can ever do with valves now, like physically, because we can't create all these huge desks easily and that sort of thing. But I think it's just depending on how you look at it. If you could, I guess if you put a solid state hi-fi next to a valve hi-fi and asked me to tell which one was which, blind, you know, might not be able to do it because it's part of the design. I don't know whether people, I don't know, it's an interesting point. If you put transistors in a valve circuit, or you designed it that way, it might sound like a valve circuit, and if you used valves in a transformer design, it might sound like a transistor design, it might sound like a transistor circuit. I just think that there was a time when, this is probably going back to 70s and 80s, there was a time when designs just weren't up to it, and I think a lot of emphasis on the quality, you know, huge amounts of global feedback just to make your figures stand up, and cost issues obviously as well, because transistors can be a lot cheaper to make.
Yeah, okay.
I think.
Why is feedback such a demon? It seems to be demonised by the Wi-Fi fraternity. It's become a very contentious thing, you know, zero feedback design, but you know, particularly in transistors, if you look, they inherently have feedback, so it's kind of a bit impossible.
Valve circuits will inherently have feedback as well. by their nature unless they're designed not to. I think there's a point of when you introduce global feedback into a circuit, it will make the circuit more stable and it will make the performance better on paper, but I think it's just down to sound quality wise, really, ultimately, and that's what we're here for. I've built a few high valve hi-fis and come from your angle and said, well, what's the point if it's going to make the amplifier more stable? Why don't I just add a load of, why don't I add 20 dB of global feedback? But then doing tests with and without, you lose you lose something. You lose.
From a subjective point of view, sort of listening panels, they tend to prefer lower feedback designs.
I'd say so, and that's if 20 people in a room agree, then it's still subjective. But I don't know. It's hard to tell, really. I don't know. It's all sound. It's all your own preference, and if you do like the sound of circuits with lots of feedback, then go for it.
So in recent years, feedback seems to have been slightly demonised in the media with, well, sort of marketing, particularly in hi-fi. And I wonder if some of these people looked at their record collections and they look at the design of a lot of classic Neve, Telefunken and all these pieces of gear that made their favourite reference recordings have all got oodles of feedback.
Yeah,
and it's kind of, you're demonising feedback in your own hi-fi, but you're playing all this stuff that, had loads of feedback when it generated the music. So
yeah, I think that you shouldn't get too caught up in things like that, though. I mean, if you took a Dscope to the equipment they were using back then, you'd be appalled, probably, or the engineers would, from a point of view now.
Depending on what kind of distortion you like.
Yeah, well, exactly. And if you go, it depends how far you go into that, really. I think the point about distortion, for me personally, is that when I've done tests and listened to varied amounts of feedback, the lower the feedback, the more I like it, and whether that's because it's introducing these distortions that make me happy when I listen to it, or this sort of, this, in the hi-fi world, this sound stage that people talk about. I think if it helps that and I like it, then you should do it, and a lot of people agree, so I think we can't all be wrong.
I would add a point on that. When you're designing a linear circuit, you design it without feedback, you do the best you can, and only when you've done what you can do, only then do you add the compromise of feedback to improve it.
Yeah, that's correct. I think some circuits, some amplifiers certainly don't work without feedback. The Mullard's, old Mullard 520s they'd go unstable without the feedback connection. And I wouldn't recommend going in and cutting all the tracks in your circuit boards because they're designed for that reason. But yeah, coming away from studio stuff, because that is different, going into hi-fi, the very low wattage valve amplifiers with zero feedback is the best you can, in my opinion, the best you can have.
Yes.
There's a question here.
So just the history of Thermionic culture, when do you start and how difficult was it getting established and things like that?
The history is all down to our founder Vic Keary, who was a record producer in the 60s, and he built his own valve desk, which I think is still working somewhere.
It is,
It is, brilliant. I think it's in Brighton, actually, somewhere.
No, it's not in Brighton.
Is it not?
No.
Where is it, in Camden?
It's in your neck of the woods, actually.
Oh, right, okay.
I'll tell you about it later.
Brilliant. I'd be interested to see inside it, because we've seen some early culture vultures and there's been sort of cigar ash in the corner and things like that. But so he built his own desk and went from studio to studio, and then we're actually celebrating our 15th year now. 15 years ago, he and Nick Terry set up the company. And we've been going since then.
Hi. You mentioned second harmonic distortion, the classic sort of low-order distortion that gives you the valve sound. You also showed the Altech schematic differential stages, and you indicated you've got some adjustments that in your products to balance out distortions on. Does that not reduce the second harmonic, especially if you start balancing the stages?
Yeah, it does.
Closer, and therefore emphasise the higher
harmonics?
Well, I think it's the higher harmonics is almost unmeasurable, really. So it's not an issue for us.
It's still dominated by the second.
It absolutely still dominated second and third, and you know that is the sound of the Phoenix. It's not just second; there is some third in it. It's just the way.
I mean, it is important. I know that, and that's the valve sound. And certainly, I build guitar amplifiers for fun, and you know, it's important to get that. But in the studio gear, you know, you want that distortion quite a lot lower.
I think essentially, inherently, valves are very linear, and transistor circuits will need a lot of negative feedback to make that higher order distortion come down. But then you're introducing all sorts of intermodulation distortions, and so I think it's touching on a point I made earlier, is the simplicity of the design using valves is the reason they still sound so great.
Sorry.
There's one more there.
I was wondering, what's the best way at the moment to test the any of your equipment to make sure that the distortion, the wear of it is not.
Oh, you mean like an older unit?
Yes. Well, I've used one abroad, and obviously to send it here back to you it takes a
well, we do have obviously a very good point, because we need to make sure that people around the world that buying our stuff is going to be as good as we'd like it to be. So we do have technical service centres, or people that tell us they can do it anyway around the world.
Yeah, that's another thing. We definitely do not have someone, so it's basically we don't trust anyone near.
Oh, where are you based?
Ibiza in Spain.
Oh, okay.
So no one. Don't trust anyone.
Should pay me to go out there.
Yeah, when someone says, "Yeah, I used to build SSLs," you say, "What, on acid?" Really not a good idea. So basically, just once every month, every couple of months, it'd be great to just be able to do a self-test, and then if we notice something changed, to be able to contact you and see what to do from there.
Again, the circuits are simple, and if you've got the equipment to test, then we can go through with that. But a couple of years' time, you might have a self-test procedure.
That sounds great. Thank you.
Okay.
In terms of noise and microphonics, I've sort of got two questions. One is, how do you compare modern valves being made today compared with Mullard, Telefunken and what have you that were made in the 60s in terms of noise and microphonics?
Yeah.
And secondly, can you sort of touch on your test procedure for selecting the valves? You use a curve tracer? Have you got like an in-house built machine? An interesting one tying in with digital and analog control is that today you can buy these computerized curve tracers, can't you?
Yeah. On the valves themselves, we still use military spec valves from the 60s, 50s.
Oh, so you use NOS valves?
We use anything we can find, really. And when we can't find decent old ones, there's lots of good new ones like JJ and Electro-Harmonics make very good valves. It's an interesting point, actually. We found some Russian valves that were dated 1988. So Russians were still making valves all the way through the 80s. Obviously worried about something. And test procedures, we actually get them from our suppliers already tested. Because we need to make a high number of products efficiently, we expect them to come in tested, and we then will see whether they can go into our unit, and some pass and some don't. That's the best way we can do it.
So you test them more in circuit? You don't
Absolutely, there's no point in testing them in a valve tester and if they're not going to work in the unit. So for microphony, we'll just hit it, and if it rings, then obviously it's more technical than that. I hit it twice or something.
As a rule, you prefer NOS?
No, I don't know. Yeah, we are the limited edition ones had the new old stock valves, but people like that when they read that they want to know their money's gone somewhere, I suppose. But yeah, if it glows and it works, then that's cool with me.
Well, JJ have recently released the famous 6386, haven't they? Have you heard much?
No, I think it costs about £100 or something.
Oh yeah, it was stupid. Yeah.
But
almost as much as a real one from RCA.
Yeah, so we find our own ways of going about that.
Okay.
We use the PCC85 in our Phoenix.
It's an interesting thing, because it's the only purpose of the JJ valve is for use in variable mu compressors.
Yeah.
And it's quite interesting that, I mean, I regret selling, I had a stack of original RCAs, which I stupidly sold a few years ago. But it's interesting that in the last 3 or 4 years, you've had a major company reissue, deliberately re-engineer a valve, the primary purpose of which is for compression.
And that's great, because it shows that there's this, resurgence, if I can call it that, in valve technology, which is fantastic for us. And the point of this lecture, really, the first time I did it was at Anglia Ruskin University, and it was a lot of students, and it was great to actually connect with the students, and we try and get our units in education facilities so they can have hands-on experience with. Obviously, we want them to buy it, but it's great that the students are using valve outboard, because we need to keep it alive.
If you went back in time 30 or 40 years and you said valves would outlive the CRT, I think people would laugh at you. But,
they may do.
The evidence is there, isn't it?
I think we've done all right.
Any more questions? I think we're done. Then we can close the floor. If anyone has anything to say to Charlie or Rob later, then I'm sure you'll be here for a while packing up.
Yeah, thanks.
Meanwhile, thank you very much. Our next lecture, to pick up on Rob's thing about the factionalisation of analog and digital, couldn't be more digital if we tried. I think I'm going to get the venue right this month. It's at Dolby's Theatre in Soho Square, and it's by Andy Farnell. It's about procedural audio, which, as far as I can work out, is a way of dynamically in real time generating realistic natural soundscapes and doing synthesis of real world objects and manipulating them. So it should be a very interesting, very digital talk. That's the 9th of April. Thank you.